Hi folks, today we are going to be continuing our understanding of how to represent atoms. So yesterday we talked about nuclear notation, we talked about Bohr-Rutherford diagrams, and today we're going to be talking about Lewis structures. So our goals for today, we're going to review what we know about the organizing principles of the periodic table, in particular about electrons, and then we're going to learn how to draw a Lewis structure of an individual atom. So first, in review, remember that we've got these rows in the periodic table. These are also called periods, believe it or not. And the period that an element is in tells you how many electron shells, which is to say how many of these rings that we have on a planetary model that element will have. So we've got the number of shells is the row that an element is in, and that's those rings. Now, at the same time, we have the groups. So the groups are the vertical columns. And we have the A groups, which are the 2 columns on the left and the 6 columns on the right. And we have the B groups, which is this whole middle section. For that middle section, we're going to ignore it and instead focus on the A groups for now. And basically, what you should know is that if you have an element in these A groups, that tells you how many valence electrons, remember valence electrons are the electrons in this outermost shell, it will have. So for example, hydrogen is in column 1A, this first column, it will have 1 valence electron. So will lithium and sodium and potassium and all the other elements in that column. Carbon is in column 4A, which means it has 4 valence electrons, as does everything else in that column. Things in column 7A, like fluorine, chlorine, bromine, iodine, etc., will all have 7 valence electrons. So by knowing which column something is in and which row something is in, you can very quickly tell how many shells you're going to need to draw if you're doing a planetary model, and how many electrons are going to go in that outermost shell. So, we're going to be reviewing. We've reviewed the structure. Now it is time for us to look at how we're going to actually draw those Lewis structures. So let's go into an example. So fluorine is element number 9 on the periodic table. Its symbol is a capital F. You can find it in the second row in column 7A. So fluorine has a mass of 18.998. I'm going to round that and call that 19. So we're dealing with fluorine 19 here, an isotope of fluorine. And it's element number 9, so it has an atomic number of 9, which means it's got 9 protons. Now, if we've got 19 as the atomic mass and 9 protons, then 19 minus 9 gives us a total of 10 neutrons. So 9 protons, 10 neutrons in my nucleus. And then, of course, the same number of protons as we have electrons. So we will have 9 electrons. So 9 protons, 10 neutrons, 9 electrons. Now, let's start drawing. I'm going to start with my nucleus. In my nucleus, I've got those 9 protons and those 10 neutrons. Again, you can just do this. Just say how many you have. You don't have to draw a whole bunch of little circles. We're just going to represent them with these letters instead. Now, fluorine is in the second row of the periodic table. That means it has 2 electron shells. So 1, 2 electron shells for fluorine. We always start with that innermost shell, which can hold up to 2 electrons. So first 2 of my 9 electrons are going to go here. So 1, 2. That means I've got 7 electrons left. So let's start placing them. Again, think about those quadrants. We've got that north, east, south, and west quadrants. We can only stick electrons in those quadrants. You have to start by putting 1 electron in each quadrant, and only once you've got 1 in each can you make pairs. Electrons like to be in pairs. So we have 7 electrons left because we've already used 2, and we've got 9 total. So 1, 2, 3, 4. Now that I've got 1 electron in each quadrant, I can start making pairs. 5, 6, 7. Now, the reason why I am being picky about these electron placements is because this electron right here, this lonely electron that doesn't have a partner, it matters a whole bunch. This is the electron that really wants to bond with another atom or get involved in a chemical reaction or create a molecule by partnering up with someone else. So this electron right here matters a lot for the properties of an element like fluorine. When it comes to chemistry and how atoms react, these unpaired valence electrons are basically the most important thing. And that's why there is a whole different way of representing an atom that basically says, you know what, you don't need to tell me how many neutrons there are. Neutrons don't do much. What if instead of drawing a bunch of circles or writing out how many protons or neutrons there were, what if you just wrote the element symbol? So in this case, this is fluorine. That symbol would be a capital F. And they say, you know, those innermost electron shells, they're always full. We know they're always full, so why bother drawing them? Let's just draw those valence electrons. And so fluorine, with its 7 valence electrons, we know it has 7 valence electrons because it is in column 7A. I can just say 1, 2, 3, 4. Notice me placing them in quadrants. 5, 6, 7. This right here, what I've just drawn, is a Lewis structure. Notice that it basically is the same thing as this planetary model. I'm just drawing the valence electrons, right? There's the 2 on top, there's the 2 on the side, 2 on the bottom, that unpaired one here. That's what matters. And this is a super quick way of representing an atom that really gets to the most important thing when it comes to, is this going to have a chemical reaction? And that is, what are the valence electrons doing? How many of them are in pairs and how many of them are all alone? That's what's going to make a difference for how chemicals react. So this is called a Lewis structure, and it's just a stripped down version of this planetary model. And that's why I'm going to make you, when you draw your planetary models, put those electrons into quadrants. It's to make it easier for you to understand Lewis structures. So just to give you a sense of something like a Lewis structure for lithium. Lithium's in the first column. It has 1 valence electron. So Li for lithium, 1 valence electron, done. Something like carbon, you'll see a lot of Lewis structures for carbon. Carbon is in column 4A. That means it has 4 valence electrons. Its symbol is C, so just 1, 2, 3, 4. Lewis structures are super quick and super easy to draw. The big thing with them is getting a hang of looking at the column that an element is in. Remember that for the A groups, that is skipping that whole big middle section of the periodic table, whichever column you are in is how many valence electrons you need to draw in a Lewis structure. So something like fluorine, it's in column 7A, so it has 7 valence electrons. If I were to draw its Lewis structure, the Lewis structure would also have 7 valence electrons, because in a Lewis structure, that's all you draw. So there you have it. That is 3 different ways of representing an atom. So we've got our standard nuclear notation here. We have our Bohr-Rutherford or planetary model here, and our Lewis structure looks like this.